Today, I talk about the optimal path planning of UAV for airborne imaging. So, as you know, the UAVs have got much attention recently for the inspection at high altitude. So today, I want to propose a method for making optimal flight path of UAV for airborne imaging of outdoor structures. So this research is a joint work with Mr. Naoki Inazu, Professor Taira Ozaki, Professor Satoshi Kubota, and Professor Yoshihiro Yasumuro. Okay, first I want to explain some background and the goal of this research. As I said, UAV are introduced for the inspection at high altitudes these days. So when we use the UAVs for the inspection, we can take photos of the target buildings, bridges, tunnels, and so on, and we can examine their situation. And also, we can use UAVs for many purposes. For example, monitoring the progress of construction, integrating as-built information, and so on. It is well known that UAV can fly and take photos autonomously when the UAVs can receive the GPS signal and photographing target is the surface of the ground. On the other hand, when UAV fly around the large structures, then UAV cannot receive the GPS signal. In such a case, UAVs should be controlled by an operator. Also, if the photographing target is something like bridges or buildings and so on, in such a case, an operator must take photos manually. For such cases, we have to make a flight plan of UAV in advance. So in such a case, the overlap between photos is very important for obtaining the complete data of the whole target. Also, the maximum flight time is about 30 minutes, so the shorter flight path is preferable. So because of these backgrounds, in this research, we want to propose a method for making an optimal path plan of UAV for airborne imaging. Okay, from here I want to explain the idea of this research. Actually, this research was inspired by our Homer research. Our Homer research is about making a 3D scan plan of outdoor structures by using a 3D scanner. So let me explain the situation of our Homer research. So this is a ground plan, bird's eye view, and this green object represents the outdoor constructions, and this red point is a measurement point. That is a point to place a 3D scanner. So in this case, we can measure this blue area from this measurement point, and we can scan these pink walls. From these figures, we can understand that occlusions make it difficult to find scanning points to cover all the surfaces. Especially, it is difficult to find the minimum number of viewpoints to scan all targets. So in our Homer research, we formulated this problem as an optimization problem. So the parameters of this optimization problem is about visibility, which can be computed based on the ground plan or the rough 3D model of the target environment. Also, the objective function is to minimize the number of points for scanning the whole target. And we solve this problem, then we can obtain the optimal scanning points. Actually, this research, our Homer research, is similar to today's topic. So in both researches, we have to cover the whole target. Especially, we have to minimize the labor and the time cost, and we have to consider the occlusions. So today's result is inspired through this similarity. Okay, from now, I want to explain the proposed method So first, I want to explain the outline. Today's result, our proposed method consists of two parts. The first part is the method for finding the optimal photographing point, and the second part is about the method for finding the shortest cycle visiting all photographing points. So actually, in this research, we assume the following. The ground plan of the target area is given, and we'll consider an optimal path in 2D space. Actually, it means that vertical movement of UAV is ignored now, and we can make the optimal path for vertical walls with the same height. So in the near future, we try to improve our method, but today we'll consider the optimal path in 2D space. Okay, from this slide, I'll explain the detail of the first part of our proposed method. So the method for finding the optimal photographing points. So first, we extract the outer shape of the target from the ground plan by using some image processing software, and we set the candidate photographing points around the target. Also, we discretize the directions of a camera on a UAV. So in this research, we divided 360 degrees into the 8 directions uniformly. And by using this, then we define the set I. I is the set of the combination of candidate photographing point and directions. This set I will be used in our proposed optimization problem later. And next, we divide the target walls. We divide and approximate target walls by line segments for making the unit for estimating the visibility, like this. So the set J is the set of the wall segments obtained by this division. And next, I want to define these two parameters, Dij and Aij, which expresses a relationship between the candidate photographing point and direction I and the wall segment J. So the value of Dij is 1 or 0. If Dij is equal to 1, then the wall J is visible from the candidate photographing point and direction I. On the other hand, if Dij is equal to 0, then the wall J is invisible from I. And Aij is the angular distance of the wall J from the candidate point I. So let me explain the detail of these parameters by using this figure. So first, I want to consider the relationship between this I1 and this wall segment J1. In this case, there is no obstacles between the I1 and the J1, and the angle of view of a camera on the UAV can cover the whole wall segment J1. Therefore, Di1 J1 is equal to 1. Also, this case, AI1 J1 is the angle of J1 viewing from I1. Next, I want to consider the relationship between I2 and J2. In this case, there is no obstacles, but the angle of view cannot cover the whole target of J2. Therefore, Di2 J2 is equal to 0. Also, the relationship between I3 and J3. In this case, the visibility is occluded by some walls. Therefore, Di3 J3 is equal to 0. We can compute these values by using some geometric computation. And finally, I can explain our proposed optimization model in this research. The objective function is to minimize the number of adapted photographing points and direction. Actually, this xi is a 0, 1 variable. If xi is equal to 1, then the candidate photographing point and direction I is adapted. On the other hand, xi is equal to 0, then the point I is unadapted. Also, this first constraint deals with the lower bound of the number of photographs for each wall segment. It means that each wall must be photographed R times at least. And the next constraint is about the lower bound of the sum of the angular distance for each wall segment. It means that each wall segment must be photographed with this lower bound b degrees. So as I said, the overlap of photos is important for obtaining the complete data. So in this problem, we deal with this overlap by setting these constraints. Okay, next I want to explain the detail of the second part, the method for finding the shortest cycle. So generally, UAV will take off the starting point and surrounding some places and return back to the starting point. So therefore, we want to find the shortest cycle of the adapted photographing points. So this problem is equivalent to the traveling salesperson problem, TSP. So TSP is one of the most famous optimization problems. So therefore, we can use the existing methods for solving this problem. However, we have to consider the specific issues of this problem. So in the TSP, the traveler can move between any 2 points linearly, but in this research, we have to avoid the collision between UAV and structures. So for this purpose, we make the visibility graph. So structures in the target area should be approximated by line segments, and we will make the visibility graph. In the visibility graph, the edges must not collide with some structures. Therefore, we omit such line segments, and we make the visibility graph like this. We'll consider we have to solve the TSP on this graph. Also, the flight path must have sufficient clearance from the structures and so on. So therefore, we enlarge the target buildings virtually for having a sufficient clearance. So by using this method, we can obtain the shortest cycle. Okay, from here, I want to explain some results by our numerical experiments. First, I want to explain the settings. So the target is a part of Al-Hamis Mosque in Kingdom of Bahrain. So this is a bird's eye view of the target area, and we choose some walls and some pillars, and we extract the outer shape of them, and we make this figure first. This is a computational environment, and the solver is optimization software to solve our proposed program. And we conducted computation for these 3 cases. Okay, this is obtained optimal points. In this case, we set R is set to be 2 and B is set to be 10. It means that each wall must be photographed twice at least, and some of the angular distances must be more than or equal to 10 degrees. So in this case, we obtained these 13 points. And next, this is result for the condition 2, R is equal to 3 and B is equal to 15. We need 19 points for this case. Also, this is a result for the condition 3. We need R is equal to 5 and B is equal to 25. In this case, we obtained 30 points. So as you see, the stricter condition we set, the more photographing points we need. It's natural. And next is obtain shortest cycle. First, I want to see this figure. These line segments is other, how can I say, the line segment between any two vertices. And these blue lines collide with the walls or pillars or something like that. And these red lines does not conflict something. So therefore, we omit these blue lines, and these red lines make up the visibility graph. So we solved the TSP on these red lines, visibility graph. And finally, we obtain this shortest cycle. And this is the shortest cycle for condition 2, and this is the shortest cycle for the condition 3. And this is the heat map. So as you see, the color of these heat maps depends on the estimated amount of obtainable data. So as you see, we can see the warmer color in this figure because the condition is stricter than others. This is the last slide. I'll touch the future works quickly. We'd like to conduct the on-site photographing based on the plan obtained by our proposed method, and we want to improve the proposed method for general 3D shape structures. That's all. Thank you.
Any questions?
Just a clarification, if I can. TSP is any, it's the solving TSP optimum. You can't solve TSP optimally. So I'm just trying to understand, you're using an approximation algorithm or something for the TSP?
As you said, TSP is a LB hard program, but in this case, it's only the 30 points or something like that. So we can solve this problem exactly.
Yeah, but then 35 points you can't.
Sorry?
As the points, a small number more points means you won't be able to solve it.
Yeah, but actually, I came from the applied mathematics division, so now we can solve for example, 100,000 points. It's approximate solution, but the gap is it's about 0.001% or something like that. It's possible. It's almost possible.
Yeah, the approximate solution, I understand.
Very interesting research. Thank you. So I have a question about I'm wondering if you have tried any commercial software that can auto-plan the path.
You mean that the software about for making flight paths?
Yes.
Yeah, we didn't do it. Yeah,
Okay.
we have to compare.
Yeah, because I'm planning to university about doing research with UAV Ultra. We are testing different tools that can auto-plan the flight path. We haven't found the best one, so I'm wondering if your research has better results than those commercial software.
Okay, we'll try. We'll try.
Every time you say the UAV, only one step or a step, maybe a few steps of UAV.
Sorry?
Every time you only set out one number of UAV. How
Uh,
this okay for about 3 steps of the UAV? They can learn from these others?
In this research, we assume that the number of UAV is just one. Yeah, yeah. But yeah, it's a very interesting question.
Yeah,
Yeah, we'll try.
it's interesting to study how multiple UAV coordinate, and some research are also doing that. But the pictures, they need to make sure that one UAV will not block the view when they take pictures. Any other questions? Yeah. So in this we also kind of looked at that, and then did you consider the resolution? So did you only look at the range, the coverage, or did you also look at the resolution requirement? For example, if I change more powerful camera, probably can take pictures from further rather than closer.
We can consider that situation by setting the parameter of this program. And this B is about the lower bound aggregate angular distance, just an angle, but this summation is about is almost equal to the resolution of the the target. Yeah. So therefore, we can deal with your situation by setting the value of parameter B appropriately, I think.
Sounds good. Yeah. Okay. So thanks again.